So for number 9, we want to prove the statement here by contradiction. And so by contradiction, if we want to prove P, we assume not P, so we assume the opposite, and then we show that it leads to Q and not Q for some proposition, Q, right? So which is a contradiction, therefore P. So what we're going to do is we're going to assume the opposite of this, and the opposite of greater than is going to be less than or equal to. That's the opposite of greater than. So we're going to say assume that n over n plus 1 is going to be less than or equal to n over n plus 2 for n belonging to the set of natural numbers. Yeah. And so because we're comparing, what I'm going to do is I'm going to just divide both sides by n so that I can remove the numerator, so that I have that 1 over n plus 1 is less than or equal to 1 over n plus 2. And then I'm just going to bring them over to the left-hand side. So 1 over n plus 1 minus 1 over n plus 2 is going to be less than equal to 0. And now what I'm going to do is I am just going to join these fractions. So I have here that n plus 1 minus, I have that n plus 2 minus n plus 1 over n plus 1 times n plus 2 is going to be less than equal to 0. And so when I do this, the n minus n, it cancels out. 2 minus 1 is going to be just 1. So 1 over n plus 1 times n plus 2 is less than equal to 0. And now I'm just going to multiply both sides by the denominator to get rid of it. So I have that 1 is going to be less than or equal to, when 0 times the denominator is still 0. And so because of this is a contradiction, right? Which is a contradiction. Yeah. So to go from here, from here, I just multiplied both sides by the denominator, which means that on the right-hand side, it's still going to be 0, right? Therefore, our assumption must have been wrong. Therefore, actually, I'm going to say the assumption is wrong. Therefore, 1 over, not 1, it should be n. Therefore, n over n plus 1 is greater than n over n plus 2. And that is it for number 9.